topic of today will be hydraulic pumps. So there is only seven including me people here at the moment, but I hope that more will come soon. But let's start. Okay. Yeah, so yesterday we talked about hydraulic actuators, and also while I was talking about hydraulic motors, I told that they are pretty similar in a construction point of view as hydraulic pumps. And now let's have a look what different pump types there are and how those pumps operate. So now we are talking about the device that is generating hydraulic power, hydraulic energy, meaning that the pumps are generating flow and also pressure. There is always some device, either an electric motor or an internal combustion engine, which is spinning the pump, and then the pump is the element that generates the hydraulic power. Talking about different pump types, there can be one direction pumps or two direction pumps. And in a drawing symbol, this pump, which is the most common one that you have seen in this course, this is called this one direction pump. There is only this one black arrow or black triangle pointing up, meaning that this can operate only in a way so that it sucks oil from some container and pumps it to this direction. But this two-direction pump will or can work both ways, so it can pump upwards or downwards, no matter the direction. And then other important thing is that there are fixed volume pumps and variable volume pumps. These, what you can see here in the picture, they are both so-called fixed volume pumps because you are not seeing this arrow. But if I would draw there an arrow like this, now it would be a variable volume pump. And same thing here. Now this would be a variable two-directional pump. And what does this variable volume mean? It means that you can control what is the flow rate of the pump during operation. Even though the shaft is spinning all the time the same speed, you are able to control the pump so that the flow that it generates is changing. So, general operating principle of a pump. In the picture, what you see here, there is a gear pump, external gear pump, and oil inlet, oil container is somewhere here, and this is pumping oil upwards. And there are two different gears that mesh each other. You see the driven one and the driver one. And while they are rotating, they are transporting small amount of oil from inlet side to outlet side. And the volumes here are such that while this gear is spinning, there will be some increase of the volume in certain stage, which generates some vacuum, and it kinds of sucks really the oil into this chamfer. And when it rotates a little bit more, then the chamfer is closed and there is this small amount of oil which goes here to the other side. And here is a different case when those teeth will mesh each other again. This chamfer volume will decrease and it forces oil to go away, which is this outlet this time. And now when I told in this previous slide about this volume of hydraulic pump, it means that how many liters or how many cubic centimeters oil is transported from one side to another side when you spin one full round. Another thing which is important to understand, that this pump is generating only flow by default, and the pressure of the system, it depends that what kind of load there is or what kind of internal resistance there is, for example, some friction or losses or things like that. So as it says here, the pressure corresponds to the total resistance of the system. So by default, you can't say that my pump is generating 200 bars, but it depends on the system that how much pressure is needed. Like you might remember, I will try to draw. Wait a minute. Whiteboard. Does it work? Now I'm working with computer and a mouse, so this might not look very clear, but I will try. If we have a chart, so that we have here this pressure, and there we have some kind of a hydraulic system, so that we have the pump, then we have some line, and then we have some kind of valves here, and maybe finally some actuator. And now if the load here is 0, it means that our pressure starts here in a very low and goes down, and maybe if there is some component losses in a valve, a little bit more down, and then we reach the target, the cylinder, but it also has some friction, so it means that we need to have some kind of pressure there as well to to beat the friction. But if we have some higher load, then the same pump will start from much higher level, go down a bit, and there is the similar drop, and then it reaches the cylinder. I'm just going to say, or the reason why I draw this is that please remember that this pump, always the pressure that it creates, it depends on what you have here. And if you have this orifice for controlling the speed, then we always start from a maximum level. Because as I hope you remember, the operating principle of this orifice is that the oil that we don't need will go back to the tank via pressure relief valve. And we need to reach such a high pressure that this pressure relief valve really opens before we can control any flow. So if there is this kind of throttle valves in a way, then it means that we will work always with maximum pressure. Okay. Then how the flow rate is calculated, or how it is formed in the pump? Well, theoretically, so that we will multiply the rotating speed of the pump with pump displacement volume, which is this V rev, or we could use angular speed and radial volume. Uh, but as it was mentioned in this previous slide, that was a theoretical flow rate. The real flow rate is always a little bit less. This text here is in Finnish, but this horizontal line is called theoretical flow rate, and this other curve is called real flow rate. And it says that N is constant, meaning that the rotating speed of the pump is constant. And why is this? The pressure is raising here, you see. So in zero pressure and the more higher pressure, the real flow rate will be a little bit less. And why is this? It's because there are some leakages, and I think it is quite easy to understand that the more pressure we have, more leakages there are. Sorry, I need to answer a phone, just a small break. Okay, here again. Sorry for this interruption. So I was telling that always in real life we don't get this theoretical flow rate because the pumps, there are some leakages in the pumps, and how much there is this leakage, it depends on pump type, rotating speed, and a pressure level. So the formula should be looking like this, so that it's not only the rotating speed multiplied by this by this VREV, but you need to multiply it also with this volumetric efficiency.
How do you get this volumetric efficiency? Is it standardized by manufacturer?
This is, to be honest, something that I think that you are not able to get the exact value, but you can have some estimate. I will later show what kind of information these manufacturers give you. And also in a couple of slides more, we will see what kind of values there are typically, what kind of efficiency values there are typically in different pump types. But to get the exact value, I think you should contact the manufacturer or make some measurements. It's not easy to get it.
Okay.
Then torque calculations. It means that how much torque we need to spin this hydraulic pump. And now there is another efficiency, not volumetric efficiency, but hydromechanic efficiency. That matters because it takes account the pump mechanical and hydraulic losses, meaning friction, different types of friction, and changes in flow speed. And it operates in an opposite way as compared to volumetric efficiency. So here, this efficiency will be better and better when the pressure is rising. And you can think it in a way that when the pressure is higher, then the oil will go to the smaller gaps and lubricate the surfaces. And in such way, there is less friction. So in a pump, you have these two different things. When the pressure is rising, the volumetric efficiency is decreasing, but hydromechanical efficiency is increasing. And the total efficiency we get when we put these two things together. So in many times, the optimum efficiency is somewhere here. Of course, now there is not an exact scale here. I don't know how much the pressure is here, but very often the curves look like, let me draw. Very often this total efficiency curves are looking like this. If we have here pressure, so that the optimum point is somewhere here. Because here we have a bad hydromechanical efficiency, and here we have a bad volumetric efficiency. All right. as I said, the total efficiency is hydromechanical multiplied by volumetric efficiency. And then that how much power we need from the pump. You remember this formula? You have used this formula in the early stage of this course, the flow rate multiplied by pressure. But if we want to find out that how much power we really need, we need to divide it with this total efficiency. So in real life, we have to have a little bit more power so that we can beat the losses what there are, what exists in a pump. And sometimes you can see this kind of characteristic curves of the pump. These curves or ellipses here in the middle, they are the efficiency levels, and you can see that in what are the operating points where you reach the highest efficiency. Here we have a pressure level, and there is a flow rate, and these decreasing, little bit decreasing lines are the spinning speeds, meaning that what is the spinning speed of the pump. And there you can see the power consumption lines. And for example, if we have a look at this point, when the flow rate of the pump is 150 liters per minute, and if the pressure level is 200 bars, we have better efficiency than 90%. And I can see also that it is very close to the 60 kilowatt line. And the power consumption is about 60 kilowatts, a little bit less than 60 kilowatts. And at that time, the spinning speed will be a little bit less than 2,000 rounds per minute, something like 1,800. Because there is the line where is this 1,000 RPM, and here is the line for 2,000 RPM. Something like this, but this is already such the information that you won't find from internet, but you need to contact the pump manufacturer, and I think that you need to give some good arguments that why you need such information. So it's not something that they will give for everyone. And I think it is this efficiency things because they don't want to so easily let other manufacturers to know that what kind of efficiencies each manufacturer has. But what we see from this picture is that it is quite a small distance from this best optimum efficiency to this very bad efficiency. If we compare that we will operate in this 50 bar area compared to the 100 bar area, we will travel to less than 75% efficiency to better than 90% efficiency. So we really need to have some pressure, or it makes sense to have more than 100 bar pressure so that we can operate in a smart area in an efficiency point of view. in a constructional way, there is a list of different pump types. Gear pump. This is called external gear pump. Another pump type is an internal gear pump. They are usually constant volume pumps, so that you're not able to change the volume of the pump. Then a screw pump. This is also something which is a constant volume pump that you are not going to adjust it. A rotary vane pump, not so common anymore. It has some problems. There are parts that wears and you need to change them relatively often, and that's the reason why this is not so commonly used anymore. Then two different types of piston pumps, an axial piston pump and radial piston pump. And if I would need to pick the most common pump type, to be honest, I'm not sure whether it is these gear pumps, maybe the internal gear pump, or the axial piston pump. If we go a couple of years back, the gear pumps have been the most common pump type, but all the time these axial piston pumps are selling more and more. They are a bit more complicated pumps and thus also more expensive pumps, but they have some benefits compared to these the gear pumps. With axial piston pump, you can have this variable volume thing, which is not possible with the gear pumps. So these are constant pumps and these are adjustable pumps. Also, you can reach higher pressure levels with axial piston pumps compared to gear pumps. And also the efficiency, I would say, it's not worse. It might even be a little bit better with axial piston pumps. But of course, the price is the thing that if you really don't need those variable volume things, then it might make sense to have this more simple and cheaper option, a gear pump. And then a screw pump. There is one special ability which makes it different compared to any other pump types. And if you need that one, then this is a solution. And I can try to show it to you. If we talk about a screw pump or axial piston pump, how the flow comes out, you can imagine that there is this teats and the gaps between the teats and the fluid is transported in the gaps. Or you can think about this axial piston pump where the pistons are moving back and forth and in that manner transporting the oil. So it will be something like this, the real flow rate. It's not constant, but every time, depending on how many pistons you have and what is the rotating speed, you have a different type of waves here. So it's not really constant flow rate. But normally it doesn't matter. It's so small waves that you don't recognize them easily. Maybe there is a little bit more sound or noise. But if you need to have a very constant flow rate and maybe more silent operation, then you might select the screw pump because it doesn't have this kind of waves at all, but the flow rate that it generates is a straight line. But the disadvantage is that the screw pump doesn't have such a high efficiency. There is more friction, and that's the reason why it is not so commonly used. Now there is one calculation for you. You need to find out that what would be the needed volume for the pump if you need to have 14 liters per minute flow rate, as the system maximum pressure is 210 bar. So find out pump displacement volume and also the information that how much electric motor power is needed. Two simple calculations based on the formulas that I introduced, this formula and this formula. And be careful with the units. I will be silent for a while so that you can try this and let's see the results. Okay, what is the situation? Are you ready?
Well, not really. I'm a little bit confused with the displacements because we have two formulas there, right?
We have two what?
For formulas, I mean, we have theoretical flow rate. Well, it's one formula, and it can be explained. It can be explained as speed of revolution, as I suppose, multiplied by the number of rotation. Oh, okay.
So this will be the formula that you should use. It's kind of the real flow rate. What is the demand? And you know the volumetric efficiency, and you know this n, the rotating speed. So this v rev is the one what you need to find out.
And what do we use as delta P in the force in the power for electric motor? Is it just?
It is this one.
Okay, I thought we need to subtract something. But okay.
Yeah. Okay, so I will try to draw these formulas here. I'm not in a normal working place, and I don't have the tools that I normally would have with me, so this will be a little bit complicated, but let's try what we get. So, as I mentioned, this is the formula that we are starting. Okay, I don't get the Greek letters here, but let's put here volumetric efficiency. Let's put it like this. F wall. I don't know if it confuses you or not, but anyway. And now this is the thing that we need to get out, this V rev. And of course, it is such a straightforward thing that we only get the Q, which was given to us 14 liters per minute, and we will divide it with the rotating speed that was also given, and the efficiency, volumetric efficiency, that was what was given. So this V rev This is not nice. Is this Q divided by N and this efficiency. Like this. And I told you that you need to be careful with the units. But what is a nice thing is that we have here 14 liters per minute. And the rotating speed was 1,500 RPMs, and RPM is same as 1 per minute. So I don't need to change anything because the minutes will simplify away. And then this was this 0.96. And we get something like 0.009 and 7. I'm sorry about this, how it looks like, but I have only my notepad and I don't even have a normal mouse at the moment, and this is very terrible to try to write down here. It's even worse than my normal handwriting, but this is the only formula that I will write today, so I hope that you can tolerate this. But now the question is that what is the unit? As we saw, the minutes will simplify away, and the only thing what is left is liters. So 0.0097 liters. And normally we will give this information in cubic centimeters. That's the unit what the pump manufacturers use. And how many cubic centimeters is this 0.0097? It is 9.7. Someone sent me a chat. Yes, exactly, 9.72. So what we get here is 9.72 cubic centimeters, like this. Is it clear?
Yes, so far.
And also, I think that this power calculation should be similar way clear, because it is the very same formula what you have used earlier. Power is this flow rate multiplied by pressure. And now if we want to have a real flow rate, we need to have this total efficiency here. Okay, now I'm not going to draw the numbers, but I'm just saying that when we are doing this calculation now, I can't put directly this 14 liters per minute here, but I need to change the unit into cubic meters per second. And I have to multiply the pressure in pascals. So I need to convert these bars into the pascals. And when I use these numbers and the total efficiency, which was volumetric efficiency and this hydromechanical efficiency, I will get a result which is something like 5,548. And now the unit is watt. So roughly 5.5 kilowatts. Do you agree?
Yeah.
Okay. All right. So if we go back here, that was the last sheet, but I want to show you from here a couple of things. At first, about these pump types, I have a link to 2 different animation about the external gear pump and axial piston pump, and let's have a look how they work it. Okay, we have some commercials. Nice. Wait a moment. Do you hear the voice?
We hear nothing yet except you.
Yeah, it's true that I don't hear anything either. But I don't know what is the reason.
I think it is a silence videos as it states in the description.
Is it so? No. This silence means it's the model. Normally there would be an people telling something about. If you mean this silence, it's the model of the pump.
Oh.
Or maybe it's some settings in my tube. Okay, it seems that we don't get this voice for some reason. Okay, then we don't get the voice. It's that simple. But I will try to explain it roughly. So mainly I wanted to show you this because it describes quite well the operation of this external gear pump. So you see these two rotating gears and the shaft which is spinning there. So the oil travels while the gears are meshing like this. This is how the pump operates. And this special pump type won't have a straight standard teeth, but it has this different shape in the teeth, which makes the noise more silent and not so much pressure shocks. You would be hearing the difference, but now you don't hear nothing. Maybe you can try later with your own computer and you will hear all the explanation what they give. Yes, this is more like an advertisement about this pump. Yes. Okay, I think that was enough for this one. And then there is this other pump type, which was this axial piston pump. And this will last more than 10 minutes. I just want to show you the main points here. You can study the operation maybe later by yourself. And I think that there are now some people that were last year in this technology in practice course disassembling and maybe assembling this kind of device. Do you remember?
I remember there was such a device, but we didn't work with that.
Yeah.
Well, my group.
Mm-hmm. So one of the groups were disassembling and another group were assembling this kind of device. So you maybe remember a bit how it looks like inside. So the main thing is that there are these pistons and the swash plate, which has some angle, and you are able to control the angle of the swash plate. And while you are doing this, you are controlling that what is the stroke of one piston. And when you can control the stroke of a single piston or all pistons, you can control that how much actually you pump the oil. And this is the key or the most important feature in this pump type. And you can control it, let's say, over 0 degrees, which means that you can change the direction at the same time. So you can very smoothly control the flow rate, both positive flow rate and negative flow rate. And now we get back to this conversation that we had yesterday, that why this kind of hydrostatic transmission in some mobile forest tractors or excavators is so easy. It's because it's so easy to control this kind of pump, and like I mentioned, it gives you very high forces easily, but of course the efficiency is not so good as with normal mechanical transmissions. But this is the unit what they use to control the driving speed. Okay, let's go further and let's see if there is an animation when it operates. So as you can see, the single piston is moving up and down, and in some stage it is sucking the oil, so-called suction cycle. And later on, the same piston goes back up, and then it's pumping the oil away. And there are many pistons doing the same circle all the time. And now I think it is easy to understand that if we change the angle here to travel, what the single piston does is this changing. Yes. But you can study this material by yourself later and take your time. I still want to show you once again this Bosch Rexroth catalog. And now we have been studying already cylinders and different kind of valves. There would be some motors, but now I'm interested about pumps. And you see these different pump types here. Axial piston pumps, external gear pumps, internal gear pumps, then special type gerotor pumps, vane pumps, radial piston pumps, well, and then they call electrohydraulic pumps. But let's keep it simple and let's study these internal gear pumps, because there is this similar tool as there were with the hydraulic cylinders. So I can configure the pump that I want based on technical data that I give. The first operating pressure in the calculation that we just did, it was 210 bar, and the flow rate 14 liters, and the rotating speed 1,500. So now there are the same specifications as here: 14 liters, 210 bar, and 1,500 RPM. It gives me two different options. medium pressure internal gear pump or high pressure internal gear pump. Other one says low operating noise and low pulsation, very good efficiency, cost effective for mobile application. Another one has more or less the same things, but it says it is more for industrial applications. Okay, let's select the internal industrial applications. Okay, then I need to specify some technical things, that what is the direction of rotation, what kind of shaft there is, how the pump will be connected to electric motor or internal combustion engine. Is it using this kind of a key, or is there some kind of a splined shaft? It doesn't matter so much at the moment. And there it is. The pump type BGH. The frame size is 3, series 2X. I don't know what it means. But then the important thing is here, the nominal size, 011, meaning that the displacement volume is 11. And what we calculated was that what we need is 9.72. And of course, just like it was with the cylinder, they are not providing every single size, but there are some standardized volumes, and this is the closest one to the one that we would need. So the displacement volume is 11 cubic centimeters. We would be able to rotate it between 600 and 3000 RPM. In our example, this 1500 fits very well somewhere in the middle. And it says that it gives a flow of 16 liters per minute with 1450 RPM with this kind of oil, which is very close to the demand 14 liters per minute. It can generate continuously 350 bar, which is more than enough. And it can produce short peaks of 350 bars. Then a viscosity range and some temperature range. And I want to have a look about this technical data sheet still. Internal gear pump fixed displacement. This is how it looks. Okay, let's have a look. So there are two different frame sizes, 2 and 3, and depending what is the needed displacement volume, it will change at some point. And according to our calculations, what we would needed would have been something like 9.7, and we can see that this 8.2 is not enough. That's the reason why the configurator gave us this 11. And we can see here also the flow, that if we would have picked this one, we wouldn't have got this 14 liters, but only 11.8. But this one already gives us a little bit more than we would need. Then there is a description on which kind of oils would be suitable. And now we have some efficiency and flow curves. So it was this NG11, our selection, and we will see that while the pressure is raising, our flow is a little bit decreasing if we spin it with the same speed. And now the reason is that the volumetric efficiency is not 100%. In the beginning, with the gyro bar, we can get, let's say, 16 liters per minute. But if the pressure would be 300 bar, then the output would be 15 liters per minute. And here you can see the efficiency curves. And now this is the total efficiency. So it's not volumetric efficiency, it's not hydromechanic efficiency, but it is the total efficiency. And you can see roughly the shape that how I described it will be, so that we will begin with not so high efficiency because the hydromechanical part is bad here, and in here the problem is the volumetric efficiency. But the optimum area is quite large, let's say starting from 100 bar to 200 bar, we can operate with very nice efficiency, a little bit less than 90%. Also, we can see the power consumption here, and we can see how close we are to our calculations. We have this NG11, and our operating pressure was 210 bars. So we would be approximately in this point, which points 6 kilowatts, and our calculations pointed out 5.5 kilowatts. So why there is a difference? There is a difference because in here we have a bigger pump. We have this 11 cubic centimeters. In our calculations, we use this 14 liters per minute and 9.7. So that explains the difference in this power. And maybe also, I don't know, how much was the total efficiency? Was it something like 0.88 if we multiply our volumetric and hydromechanical efficiency? So it could be quite close to this situation. But do you now see this connection between this information and the calculation that we just did?
Yes. Yes.
So we basically don't need to calculate this equation if we have these graphs.
Mm-hmm. Yeah. All right. But I think this was everything that I was planning to tell you today. And now, if you have something that you want to discuss with me related on your design exercise, now it's time for that.
Can you create a breakout room?
Yes, I will do that.